it's at 1 p.m. and 3 minutes past. So should we start it?
That's fine with me. I'm just trying to get my computer up here so I can show you guys some. This is like, oh, okay, yes. Okay, I'm seeing it.
So why not I see two of you?
Yes, that's right. My phone has much better camera and audio. So I'm talking to my phone, and what I have like directly above my phone right here is my computer screen that I'm going to show you all the goodies. So at some point I will ask to share screen, but we can go as it is now.
Okay. Clark, do you have some slides? Would you like to test the screen sharing option?
Sure. Let's try share screen. Just a moment. I put together a bunch of goodies for you all. Let me see if I can share this. Trying to share now.
Yes, I can see your.
Okay. Yeah, it works.
Okay.
Good. So
yeah,
I will start just by giving a brief introduction. So let me first share some slides prepared by Helen, and we'll start soon. Okay, can you see my slides now? Okay, I think we can start. So the meeting is now recorded. So let's start officially. Hello, everyone. Welcome to the next meetup organized jointly by quantum computing groups from Washington, Toronto, and Warsaw. My name is Pawel. I'm one of the organizers and CEO of the Quantum AI Foundation and coordinator of QPoland. Together with Dr. Sebastian Zajac from QPoland will be the moderators. And today we have a pleasure to host a great speaker, Dr. Clark Alexander, and he will give a talk titled Painting Quantum Pictures with Walks on Graphs. So before we start, a few announcements. So as you can see, this lecture is recorded. So the video will be later available on our YouTube channel, hopefully. Clark, maybe just a question regarding asking questions. Would you like to have this meeting more interactive so that the participants could interrupt and ask the questions, or you can also just organize a Q&A session at the end?
It kind of depends on how everyone's feeling about it. I'm happy to do either. I think probably easier. I go ahead and give about 30, 35, 40 minutes of fun goodies and tell you kind of what I'm doing, and then open it up to questions, and everyone grill me as much as they want and ask as many hard questions as you want, and I will fail to give as many answers as possible.
Okay, great. So maybe just a request. That sounds good. So just a request to our participants, if you have any questions, feel free to post them on our chat as a message, and then we'll just ask these questions later. Okay, so just a few announcements before we start. We'd also like to invite you to our next meetings. So next Saturday, Jitesh Lalvani will tell about quantum for space. In 2 weeks from now, Dr. Joaquin Matras will tell about GDS Factory, an open source Python flow for circuit design, verification, and validation. Then in November, Jerne Rudi Finsgar will tell about new approaches to near-term quantum optimization. Then in December, Tim Linke will tell about gaming for quantum literacy, modern approaches to quantum information advocacy. And then in January, Dr. Anup Krishnan will tell about accelerating materials discovery with AI and machine learning. We'd also like to thank our partners and sponsors for supporting us and making this event possible. And with this, I will stop sharing my slides. And Clark, if you are ready, the Zoom is yours, and you can also start sharing your slides.
Sure. I'll give a second. Thank you, Pawel. Thank you, Sebastian, for hosting, and Helen for organizing. Thanks to QPoland, all the relevant parties. Many thanks. I just want to take a quick moment to acknowledge outside of quantum right now, there's a lot of sort of suffering happening in the world, and I just want to take a moment to recognize that even though there's a lot of attention being placed in Israel and Palestine, that there's other people suffering right now, and that's weighing a little heavily on me. So just take a moment to recognize that. All that being said, this talk I want to be a lot lighter. I want this to be a lot lighter. This is something to be a little bit fun, right? I think a lot of the talk around quantum computing recently has been, oh, we're doing quantum supremacy and quantum advantage, and we're trying to like make these cool gate models, and everyone's trying to build this hardware, and then Flatiron Institute's like, we can do it with the digital computer, and there's all this stuff going on. And I think I don't want to talk about any of that. I just want to do something fun and lighten the mood here a little bit. So in general, to my understanding, there's really, let's call it 4 paradigms of quantum computing, right? The first one that sort of came out on the market was D-Wave's annealing, quantum annealing computer. And everyone and their brother has been trying to build up gate computing for a while. Meanwhile, ID Quantique and some of these guys have some random number generators, and Erica Grant has a cool company called QLock. And so that's like 3 separate things. But this one that I really like to play in is quantum walks on graphs. And so Andrew Childs at University of Maryland showed back in 2008, 2009 that this is also a universal model for computation. But we don't really have the hardware to do universal computing. So I decided at some point, let's do something entertaining, right? If being in industry as a mathematician has really taught me anything, is that it is really difficult to talk to people about what quantum computing is if it's not entertaining or flashy or something you can do really quick. So a couple of years ago, 2 friends of mine here in Chicago, we partnered with W Series, which was a racing series supporting Formula One, and there was a team called Court DAO. That's a community-owned racing team, and DAO is Decentralized Autonomous Authority. They were going to be a crypto-funded team, and so we made them some NFTs. And to my mind, this is the first and only triple combination of female motorsports, quantum computing, and cryptocurrencies. Right? That's it's just a thing, and we just thought this was going to be entertaining. So let me show you this. This was one of the NFTs we made. It never made it to market, but if you can share and see this share. I don't know how clearly that's coming through. It's a little bit blocky, but this was the helmet of Marta Garcia, who is currently leading the F1 Academy standings. We hope next weekend she'll win it all, because we were way back on her team first. But what I've done here is I've taken an image, and the way essentially that I'm talking about quantum walks on graphs is I'm taking this image and I'm wrapping it up either as a torus or a cylinder or a real projective plane or a Mobius strip or a Klein bottle. You can wrap it up in any way by gluing the edges, right? Some basic undergrad topology. And so what I do is I take every image intensity as if it's a probability or amplitude in a quantum walk, and then I just evolve it by some unitary matrices, and then I just display out the intensities as another picture. And then I stitch them together with FFmpeg, and there you go. And this is how I do quantum painting, right? More or less this. Let me show you a couple of other goodies. Some other fun things you can do with quantum painting. too many things open here. Let me share this image with you. So I'm in Chicago, and here's an image of our skyline. Okay, if you look in the water, those waves were created by a quantum walk on a graph. The image is actually it was actually still. Here's the original image. This is the image of Chicago's skyline, and then I quantum walked just on the water. I figured you should make waves in the water, and here I've sort of touched up with quantum painting the water. All right, so what I did in this case is I cut out the bottom part of the image and I turned it into a cylinder, and I just walked it a couple of steps quantum mechanically, and there you go. You see waves in the water as if they're water waves, but these are actually quantum waves that I'm just displaying out, having walked on a cylinder. Okay, and then just get a couple of other goodies. You can see some of these things. I've put two images back to back. Here I've rotated 17 pi over 4 steps on a cylinder. And I was trying to work with McLaren's Formula One team and IndyCar racing team. I made an NFT where I swapped these two images by, just they pass through each other, although I don't have the image of that. I don't have the movie of that ready to share you guys today. And here I took, this is a Lisa Zhu figure made on a spectrogram, and then I just walked it out so you can see how like the waves are interfering at the intersections of position, not in time really. Something I've been working on this week. This is the wave intensities of walking across a graph. This is a cyclic graph of 101 vertices. And if you were to think about a classical random walk where you're flipping heads going left and right, left and right, left and right, you're going to have a big binomial distribution centered here. And this one, you can see the waves start propagating after about 101 steps. So I thought this was a pretty nice little demonstration of what happens. This little guy here, I believe to be the very first real discrete time quantum walk on an image with 4 picture channels. So actually not only connected the red, green, and blue individual channels, I connected themselves with a graphene type structure. So this is a 5 regular graph. Here I just picked some random quantum effects, and so it's just blinking around and giving people seizures. So I just wanted to try to do that while I could. So okay, so there's a couple of fun things. And over the next few minutes, I want to tell you kind of how I do this, and then I will share for you in real time. I'm going to paint something for you, which I will try to make available. Everyone will get a little GIF and .mov file or .avi file of what you want. I'll talk with Pawel and Sebastian to distribute this. It's my little present to you. It's a quantum painting that I'm going to make for everyone, but I want to do it in real time just to show that it's actually kind of fun. Okay, so everyone good so far? Any questions? Any questions as of yet?
Mm-hmm. There are some questions.
I have a question.
Great. Go on.
And sorry, I'm outside. Can you do also the inverse, taking real waves image and translate them to your random graph, random walk on your graph?
Well, so yes, you can do this. The way that I'm thinking about this, though, is the graph for me is just every vertex is a pixel in an image.
Clear.
Yeah.
Clear. However,
okay. Yeah, go ahead.
However, my question has something else deeper, in the sense that maybe you have stumbled on a very elegant solution to many difficult inverse problems.
Maybe
science fiction
that would be a fun stumble. it wasn't my intention, but that would be a fun stumble, wouldn't it?
Absolutely.
Well, contact me. I'm certainly happy to talk about that in depth, see what we can do.
That will be cool. I'll see your file and everything. Thank you very much.
Yeah, very good. Okay. So,
I have a question.
please.
Yeah, how many channels can we have with quantum computing?
I don't know. I'm using 3 and 4. Just that, although I was in Mexico this summer, Oaxaca. Here's my playing in Qubits de Ciencia. It's a nice program. If you've not taught, you should apply to teach next year. It'd be great. We were doing multispectral images, so I have an image with 33 channels. I guess I could. No, I certainly can walk on it. There's no problem there. It's just tying it together. It's a lot of pixels. So, you know, it's 1,000 by 1,000 by 33. That's a lot of vertices to handle with just a laptop. I can do it though, but it just takes a little while. So, I mean, multispectral images are a pretty interesting thing to play with. One of the next things I'd like to play with is just considering the red and green and blue channels as a triangle. And so you can discrete walk or continuously walk on these channels and sort of move it, and you get this really interesting psychedelic effect. I have to figure out how to broadcast it across every pixel correctly. But that's one thing I would like to do, to have more play with the colors rather than just the image itself. So in principle, as many as your computer has memory for. Fair?
Thank you.
Okay, Clark, we have a few more questions on our chat, so it's up to you whether to answer now or at the end. Maybe
Yeah,
I will
let's take a couple and then
let's maybe ask at least one more. So this is a question from George. Is the graph the connections to neighboring pixels?
Okay, so this is a fun fact. We'll talk about this in a minute, but for the continuous time walks, either directly connected or I can make it further. I can connect 2 or 3 or 4 vertices down. There's a trick to get it to actually run fast in continuous time walks. In a discrete time walk, you can do it however you want, just as long as you've matched up the graph. And there's this interesting piece of combinatorics which I've written about somewhat extensively. I have a couple papers on it called consistent rotation maps on regular graphs. This was originally built up for like these nice expander graphs where O and Z, I forgot their last names, took 2 graphs, and instead of a Cartesian product, they made a thing called a zigzag product, which gives a really nice spectral expansion of the graph. And so the whole reason, that was kind of the whole reason this thing started. I was thinking, oh, well, it's interesting. If you take a classical random walk on a graph, the variance is very slow. It's approximately t, right? So the standard deviation is root t, the number of steps you take, right? So if you flip a coin 1,000,000 times, you kind of expect the overall result to be 500,000 plus or minus 1,000, right? But then I started playing this quantum walk on a line, just a line of 100 vertices. And after 100 steps, the variance is like t squared over 2. So your biggest probability amplitudes are plus and minus 71. And I was thinking, whoa, that's mind blowing. You can speed up or slow down a wave with this coin. Okay. And so there's this is an active research project I have right now, is how do you actually tune the variance? And if you're given a unitary matrix, which is going to be our coin space, we'll talk about this in a moment, you can adjust the angles. You can sort of tune the angles to it. And how does that affect the variance of this walk, right? So this is going to have sort of broader implications in network theory, cybersecurity, a lot of places where you have networks of connected things. Now, if you can propagate a wave on them, but you can control the speed of the wave just by some angles. I mean, this actually ends up being kind of how electricity prices are set, which we can talk about way later, but it's an active research area for me. So anything else before I sort of tell you what I'm actually doing here?
I have one more question.
Sure.
is it possible with this procedure to combine multiple images in 2D plane into?
Oh yeah, this is one of my favorite things. And in fact, actually, the first thing I showed you, Marta Garcia's helmet turning, I took the side view and the front view. I ran one forward and one backward, and that's how I merged them. Yeah. And I use Julia for my programming language, and combining images in Julia is literally as simple as adding image 1 plus image 2 over 2.
Is it possible to do it with MATLAB?
Oh, almost certainly. So slightly further afield from quantum computing, I love MATLAB's numerical engine is awesome. Julia's engine is equivalent, more or less, to MATLAB's engine. There's a little bit of syntactical difference. The syntax is a little bit more modernized, but almost everything you can do with Julia, you can do just as easily, exactly as easily in MATLAB, minus the slight syntax update.
Thank you.
For sure. Okay.
All right. We have a few other questions, but I think we can go ahead and
let's talk about some quantum walks on graphs, because this is my fun playtime here. So the first thing is, let's maybe go all the way back to what's a classical random walk, right? A classical random walk, I'm just going to go very simply on a line, right? We're standing on some sidewalk, which is broken up into bricks. The classical random walk, the one that we observe sort of in stock prices, is you flip a coin, and if it lands on heads or eagles or wherever you're joining me from, if it lands on one side, you step to the right. If it lands on the other side, you step to the left. Right? That's a classical random walk, and you flip this and you repeat this process many times. Right? From the quantum computing perspective, what is this saying? That is, flip a coin, measure, then move. Right? You look at the coin, you determine if it's heads or tails, and then you move. Right? So you do the measurement in the middle. Right? So it's process, measurement, collapse it, move. Quantum process, collapse it, move. Quantum process, collapse it, move. Right? That's a classical random walk. Now, if we want to do this on a quantum in a quantum mechanical setting, well, we have to allow the waves to interfere with each other, right? That's kind of the whole interesting piece of the quantum effect. We want constructive and destructive interference of wave amplitudes. So we just switch parts 2 and 3. You flip a coin, a quantum coin, and then you evolve the wave, and then you flip the coin and you evolve the wave, and then you flip the coin, and then you evolve the wave, and then you flip the coin, and then you evolve the wave, and then you measure. Right? And that gives us radically different behavior. Right? So that's how it works. Now, again, because we're in the quantum mechanical setting, we're restricted to not bouncing around the space that we're moving around in isn't just a graph. We're really moving around in a Hilbert space. And the Hilbert space for me is the span of each vertex represents an orthonormal basis vector. Right? So if I have a graph of 3 vertices, vertex 1, vertex 2, vertex 3, they each get their own orthonormal basis vectors. And so that would be inside C3. Right? So vertex 1 would be represented by the vector 1, 0, 0, vertex 2, 0, 1, 0, and vertex 3, 0, 0, 1. Right? Now, each of these has 2 connections, and so our coin flip is going to have 2 sides, which means that it's just a unitary matrix in 2 dimensions. Right?
Clark,
yes.
Just a quick question, because
Please.
there's a confusion from the participants.
Sure.
Is there a screen sharing going on now, or do you have any slides to share now? Or
I do not have my screen shared right now. No, at the moment I didn't.
Okay, but do you have any slides that you would like to share now or not?
No, not just yet. Give me just
Not
a couple
yet.
moments, and I'm about to share. And
that's fine. Okay,
Yep.
Perfect. Thanks.
I'll be painting for you in just a moment. But
Okay.
idea is this: in quantum mechanics, we have a Hilbert space representing the graph, and we have a Hilbert space representing the coin flipping. Right? In classical mechanics is a lot easier. So we have an overall unitary matrix where we act on the coin, and then we shift based on sort of the graph adjacency matrix. It's a little more complicated than that, but that's kind of the idea. This is a discrete walk. So you want to walk 2 steps, you apply this unitary twice, then measure, then walk. You want to walk 100 steps, you apply the unitary 100 times, then you measure, then you walk. Right? That's a discrete time walk. The continuous time walk on a graph is way easier, tremendously easier. So if anyone has worked with graph evolutions, all you have is this thing called a Laplacian on a graph, right? It comes directly from, the Hamiltonian operator in quantum mechanics. Laplacian on a graph is just the degree matrix minus the adjacency matrix. You exponentiate this and move, right? So e to the I times real matrix is always a unitary, because you can invert it by e to the minus I matrix. So on a continuous time, you just have one unitary matrix, and then you build on the graph. Now, here's the trick. For a continuous time walk, I don't want to treat every pixel as a unique thing, because I'm going to show you in just a moment. Actually, let me start sharing. Here's my fun Julia thing. This guy up here. That's a very tiny image. It's only 173 by 291. And it's about 5 thumbnails size. Well, multiply that, you're going to be 50,000 vertices. And this is just a black and white image. To build a unitary that big is going to be a bit painful on your modern computer hardware. I mean, I have one downstairs that is a half a Google server size, and it can do it, but still not even super fast. So here's the trick. If you've had to solve systems of linear equations before, you might have come across the Sylvester equation. Is anyone aware of the Sylvester equation? All right, so Sylvester equation, it turns out it's like, if you want to solve a system of linear equations, but you're multiplying on both sides, you're trying to solve for some matrix X, you have A times X times B equals matrix C. Right, Sylvester equation gives you a way to reconstitute this, and then you can take the middle matrix X into a matrix of vectors, and then you can tensor A and B, A transpose and B, and then you can solve it out as just a single linear equation. Same thing here. What I want to do is in my graph over here, I want to take every column, and I just want to treat it as a single circle. That's very easy to quantum walk on. And then I want to take every row, and I want to treat that as a different circle. And so what I'm going to do is multiply 2 unitaries. You can see this over here. The idea is our image is rows by columns in size. We use 2 tiny unitaries. U1 in UR and U2 UC. Okay, so our final quantum walk looks like this: U1 times image times U2. And then we rely really heavily on the fact that matrix multiplication is associative. So that's exactly how you evolve it. And this is how I scaled it up to do, like, I've done quite large pictures. I've done, pictures which can be displayed in 4K, and you can quantum walk them actually quickly. It only takes, fractions of a second in Julia to do this. Word to the wise, skip this in Python. Bad idea. It crashed my computer. I have a strong computer, and Python crashed it a couple times because it's way less memory efficient. So skip. Go to MATLAB. Use Julia, Scala, F#, whatever. Pick another language. I prefer Julia, but because it's got that memory built in. But here's my quantum walking. So should we play? Let's look at this guy here. I've already loaded up for us this image. So first of all, I want to get this row Laplacian. Row Laplacian. I have a little function, get torus Laplacian, size. So here's my Laplacian. You can look a little bit closely in here. the degree matrix is 2. Everything is connected to 2 vertices, the one left and the one right. And as you go around a circle, you have left and right and left and right. So vertex 1 is connected to vertex 2, and way out here, vertex 173. Okay, so this guy is a 173 by 173. This is my matrix Laplacian. That's going to operate on the rows, and my column Laplacian is going to be exactly the same. Take the columns. There it is. For what it's worth, I got this question earlier. If I wanted to just connect everything left, right, up and down, I could do that. Or in this case, I could connect 2 vertices each direction. Have that built in. So, you can have direct connection and jumping a little bit. That gives some more interesting quantum effects. But for the sake of ease, let's keep it at 2. Okay. So this is my image intensities, right? You see these zeros represent black, the ones represent white, and then there's a little bit of gray closer to the center. Okay, so all these numbers are representing is 0 is going to be black, 1 is going to be white, and anything in between is just going to be the grayscale image. Okay, how gray is it? So gray 0.5. Right, so that's what 0.5 looks like, and let me show you what 0.75 looks like. You can see that's all that's happening here. 0.5 is basically a charcoal gray if you have a nice suit. Okay, so far so good. That's all these numbers represent. Now, what I want to do is I want to walk this guy. Let's walk it for time pi, shall we? There's my image intensities, and now let's just display it. There's our first quantum painting. Everyone able to see that? Okay, and then so we can play with this. What's interesting is you can do this, it's just a unitary, so I can go 1 step backwards. I can go 100 steps backwards. One of the nice things about quantum mechanics and time is that time is technically reversible in a quantum system, especially a stationary one, and that's exactly what I have here. So let me just do a couple fun things for us here. Go 0, give me the original image. Go 1 step, 2 steps, 3 steps. 4 steps, and now let's go back up to my Julia. You can sort of see the waves evolve, right? So what we're looking at is these white pixels are very, very, very strong amplitude waves. They're all the way up at 1. And the black waves are all the way down at 0. So you have this it's almost like the finite well. So you see these white waves start propagating down, but then they start getting some interference in here. Go all the way, let's go 10 pi steps. And so a lot of interference happening here. You can sort of see these waves constructively and destructively interfering here. So in the middle, right, the white and black have more or less mixed. And so you have this gray scale going on. And if you look very, very closely, and I'll try to get this some images to you, Pawel, if you can help me with that, you can really see these waves interacting very, very, very discreetly at the pixel level. All right, so it's really, really cool stuff. In Julia, some interesting pieces you could do with this. Let me just call this image 30. Yes.
I'm sorry for interrupting you.
No, please go ahead.
Yeah, I have 2 questions actually. My first one is that is it possible to equalize an image with the quantum painting? Or also, is it possible like to change a color image to a grayscale?
Oh, absolutely. Yeah, for sure. For sure, you can color it or you can gray it. I mean, this is something I like in Julia here, but I'll just give you an example. So color view. Shall we turn let's turn the black parts into red, shall we?
Yes, that would be great.
Thank you.
Yeah. A little bit minty for me, but you know, that's how this works. Now let's turn those green, shall we? Right, that's the other kind of mint. Very Christmassy. Yeah, so far so good. Other questions? Let me show you another way that I've actually built this out. If I just want to walk on the columns, I just give a unitary here. So you only have a left and right interference here. The up and down, I've made this picture into a cylinder, not a torus. Okay, and similarly, if I wanted to walk on, let me make it a cylinder, a horizontal cylinder. All right, you can see the wave interference is just horizontal, which you can like very, very distinctly see on the upper and lower boundaries of this image. All right, so think you have some sort of carbon nanotube. Right, so in continuous walks, in order to make this like at scale, we have to play this thing where you're really only working on cylinders and tori. In the discrete case, the mathematics is a lot more complicated, but there are a couple of designs that I'm working on. I'm working on a hex lattice. I'm working on trying to how to like a knight's move in chess. So I want to have an 8 regular graph. So you don't nothing is directly connected. It's connected 2 over and 1 up in all directions. I'm also looking at some designs that I picked up from like spectral sequence diagrams. If you remember your algebraic topology from grad school, like the next page is going to be like the next sheet of a spectral sequence. They all give radically different behavior. So this is pretty interesting. And then again, the active research is on how much can you affect the variance by tuning what your quantum coins are. So let me play one more game with you here. Let me make my row Laplacian something different. I'm going to connect 6 vertices. So vertex 1 is now connected to vertex 2, 3, and 4, and on the other side, 171, 172, and 173. So one step looks very, very, very different than the previous one step. What you can see is here you have like a dominant form, and the way that we view it is that like the vertical interference is a lot more than the horizontal interference, but that's because the vertical is what's operating on the rows and the horizontal interference is what's operating on the columns. And again, if you look very, very closely over here, wish I could resize this. Let's see. Let me resize this for you. Yeah. Down on the bottom, you can see these waves propagating 3 times as fast as you can see the waves propagating here on the left and right. Right, so there's a lot of interplay you can do, and you can just make these things work. So now, shall we give ourselves a nice picture to take home? Just a moment. Let me. Give me just a moment. No. Oh, hold on. Back in business. Okay. Another thing, another present I'll give for you. I'm going to put this code on the GitHub, and I'll just give the link to Pawel and Sebastian, so you can just play with it yourselves. Right. Get my channels. Get torus Laplacian. Walk. This is all the continuous time stuff. I have the grayscale and the color images ready. So let's make ourselves a little video, shall we? How many steps should we go? Let's just go 200. Let's go to 314. Let's go pi 100 images. Why not? That sounds fun. And back in my other file, which you can't see right now, I just see like the images just really, really, really quickly coming up. So what I'll do for you is I'm just going to stitch these together with a little program called FFmpeg, if you're familiar with that. So the whole process here is quite easy. You do the continuous walk, you make a whole bunch of frames, you stitch them together, you have a movie. There you go. That's the game. I'll stitch these together at, what do we look at? 30 frames per second. So we'll have about a 10-second image, 10-second movie. Almost done. We're at 300 images, 15, 16, 17, 18, and there we go. 1 minute. So it took us a minute and 10 seconds to do all these quantum walks. And the way I have it set up, by the way, I should just mention that I've done this quite inefficiently. Every frame I just do from scratch. I feed it the new image, I feed it the full row and column Laplacians, and I make it exponentiate that matrix a bunch of times. I'm making several formats for anyone who wants to see them, different formats. Okay. And let me share with you now, one more. Let's see if this. Are you seeing this motion? You're not seeing this motion. Let me share a different thing. And here we've painted our image. You just see these nice quantum mechanical waves interfering with each other. What I'll do is I'll make this available. I'll clean it up a little bit, and I will make it available to for Pawel, Ellen, Sebastian, all to share out. If you want to see this, this is my gift to you. It's my painting for you. With that said, I'm happy to take questions at this point. We're about 45 minutes in, so I'm happy to take questions for the rest of the entire time.
Great. Thank you. Fantastic. So first of all, thank you, Clark, for this great presentation. So we are impressed. And there are several questions on our chat. So the first question from Ron. So let's start from the end. When you walk a row or column, does it affect adjacent rows or columns?
No, but our eyes make us think it does. Right. That's kind of the fun trick in painting is, right, the rows are so tiny, right? What I just showed you is 273 rows or 291 columns. So if you walk on one column and you walk on the column next to it, they're so close in intensity that it looks like they've moved together, even though the way that I've set it up, they actually are moving independently. Our brains like to stitch it together so we see the continuous motion, but mathematically, that's not what's happening. That's what's only in our brains. When you walk both, then they're all connected.
Okay, there's a question from Dev. Is it possible to make a video because fast repeating of image form a video?
Yeah, I have a video and I will send it out. I will send it out to you guys.
Okay.
I need to cut off one column because it doesn't want to make an odd number of doesn't want to make an MP4 or a movie out of an odd number of columns. So I will subtract one column and redo it and send it out.
Perfect. There's another question from Peter. Does this walking require qubit perfect fidelity?
No, I'm not using qubits at all here. I think before I get myself in any trouble, I just don't see quantum hardware doing this at any point. This is quantum mechanics done on a very, 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 very tiny Hilbert space so that we can actually do it. And obviously there's no perfect fidelity in numerical systems, right? Let me see here. I have a matrix that I tried. This is a unitary matrix, but you can see it should be a bunch of zeros. Oh, I'm not sharing. I have a unitary matrix that I was working with before we started, and like when you multiply a unitary matrix by its Hermitian transpose, you should get identity. But what I get in the second item is 8.17 times 10 to the negative 17 minus 1.34 times I times 10 to the minus 16. So it's like these extremely, extremely, extremely tiny rounding errors. And so one, I don't have perfect fidelity, so it doesn't require perfect fidelity, but I don't know that qubits can do this because the interesting thing is in the discrete time walk, which is a lot more mathematically intense, you'd have to be able to entangle, I can have it entangle up to, like 100 qubits at a time. And I don't know if we have entanglement of 100 qubits. And even so, we'd need like a 900 qubit computer to get this error correction, noise correction. So no, the whole point is like we can like play with this and actually have fun with quantum computing without actually needing a quantum computer. That's kind of the enjoyment for this.
Okay, there are some further comments and questions. So first, a comment from Jarek. In any case, here's an animation for electron simulator with this MERW. So this is maximum entropy random walks, I believe. And there is a link to details, which is good. Jarek, would you maybe also like to give some other comments?
Hi. Thanks for the very, very nice talk. So I just wanted to tell them that you might find it interesting. There's also this random walk, which is kind of classical, but gets statistics of quantum. So I put some comments in the chat. I already discussed also if you find it interesting.
Okay. Yes. So there's another remark that there are also usually better graph Laplacians based on this entropy maximizing. So maximum entropy random walk, and there is also a link to this paper. So thanks for this, Jarek.
These are awesome. There's a whole lot of really fun ways that you can play with the graph Laplacian. I try to do it like as simple as possible because like the way to compute it, you'll see. I'll put this up on GitHub. So even in Julia, it takes, let's see, it's 2 lines. It's 2 lines to build up a Laplacian or 4 lines if you have to give more things. So like without having to maximize entropy. I mean, I've played with a lot of ones where you have like this Boltzmann distribution or you use Dirichlet S functions to like cut off the maps. Like it mixes it a lot, but the visual effect is not as good, in my opinion.
Okay, there's another question from Ron. When using a Hilbert space with so many dimensions, are you utilizing sparse matrix techniques?
You know, it's funny. I don't. When I get to the discrete walks on bigger things, you're going to have to. The nice thing is that, you know, even on my little laptop here, the memory allocation is so efficient in Julia that I don't have to worry about that, thankfully. I know that there's some really good support for sparse matrices, but I'm just not using pictures that big.
Okay.
Just not using them that big.
There is another question from Ron. Can this be used for image comparison or image alignment?
I don't know. I don't know, but I invite you to play with it and tell me.
Okay.
Yeah.
Great. So there's another question, this time from Barry. Can you go into detail a bit more on what you've done after you have formed a Mobius strip and then taken the intensities as amplitudes?
Oh, absolutely. Absolutely. So this is a little bit easier to describe just, you know, verbally. What happens is if you have, let's just take a grayscale image to make things like super simple, right? I have an image which I'm representing as a matrix, right? So let's say my image is 50 rows and 100 columns. What I want to do is on the left, or everywhere within the image, I want to make a connection of row column to row +1, row -1, column +1, column -1, except on the very, very, very right hand and very, very left hand side. I don't want to connect to row goes to row +1, column +1. I want to go to row goes to row +1, 50 minus column +1, right? So I just flip. That would be actually on that'd be a Klein bottle, but now if we're just doing just a Mobius strip, row is connected to row +1, except on the left and right where it's connected to 50 minus row.
Okay.
That's
Good.
literally it. Building up what these things are called consistent rotation maps. I have a couple papers which you know, I'd be happy to discuss. There's some like funny combinatorics. I think I cracked it in the last week trying to work on this to build it up for a Mobius strip, but I have not yet implemented it, so I didn't show it to you.
Okay, there's another question from Ron. Do you have an example using a tiny image such that you could visualize the associated graph?
Yeah, right at the beginning, I'll actually share some other stuff with you. I have a little tiny 5x5. So it's a 100 vertex graph. It's 5x5 and it's 4 channels, red, green, blue, and alpha. And I connected all of the channels together. It goes a little bit too fast, but I can, you know, I will say this, give myself a plug. You should connect with me on LinkedIn because I've been posting these things as I like find them, and it's like, oh, hey, here's a fun thing. So I've put a bunch of walks and fun pictures on my LinkedIn. Super happy to discuss at any point. I did put some stills of these little 5x5s and how their interactions are to the next frames.
Okay. Could you maybe paste a link to your LinkedIn profile here on chat, maybe together with a GitHub link?
Happily.
Because there was also a question about the code, so I understand that you will also share it with us. There was also a question if you are using a particular quantum library in Julia.
No. The only thing I'm using here is linear algebra and images.
Okay.
And I'm trying to build it up straight from that, right? Which is more fun. That's kind of the fun of it, you know. I'll give another plug. I have this program that's very close to my heart because one of my former students started it. It's called Qubits de Ciencia de México. So there are these 1 week intensive courses where you go to Mexico and you teach a week of science, basically 1/4 worth of college course in science. And I did like image processing this year and Arduino building. And we kept it as simple as possible because some of the students are in high school. And so it's this sort of fun to actually just go in and say like, okay, you need to import images. And this is how it works. And then all the math, you make them build out one by one. And I've done that here to make it as simple as possible for all. So that's
Mhm.
That's what I'm sticking to. Okay, I'm gonna post my LinkedIn here. And I
Thanks.
have not yet put my GitHub, I have not put this code in GitHub, but I will. So let me
Alright.
post on my GitHub also. Keep those questions coming. I'm into it.
All right, thank you. Do we have more questions? I think we've already asked all the questions on our chat, but maybe someone would like to unmute and ask or give a comment.
Yes, I put a short question on the chat.
Mhm.
Maybe you didn't see it, Pawel.
Yes, yes.
But the question is maybe too generalized, but there are examples. Can you simulate physics or even chemistry by your method? Have you tried something like that?
I'm banking on it actually. Another area of active research. I think Keeper's on here. Keeper and I are working on trying to simulate rigorous electron transfer properties over three regular graphs, in particular a dodecahedron or a buckyball, right? So these nice three regular graphs, which are kind of small, but graphene is this really interesting thing because it has it's not really a three regular graph, it's a four regular graph because you have this double bonds going. So we are working actually on trying to simulate a rigorous electron transfer property over a graph with exactly this technique because I mean, I think this is the point. What we're doing is we're dropping a wave on a graph and seeing how it propagates across the graph. And right, so what the hypothesis is that you should be able to measure at the end the path of least resistance. And if you can tune in a discrete time walk these angle bumpings, you should be able to speed it up or slow it down. Right, this is the hypothesis, and we're not too far into the experimentation, but the implementation is there. So
Wonderful.
I'm banking on it, but I do not have rigorous proof for you yet. But would be happy to discuss and stay tuned.
That's wonderful. One interesting example could be if by your methods you can predict the magic angle of 2 degrees in solid state that you mentioned, graphene. If I superimpose 2 layers and just deflect them from one another in 2 degrees, I get magic phenomenon.
Okay.
So
I'm into
that will
this,
be
so.
fascinating also. Excuse me. I'm outside, it's a bit chilly here. So they are talking about new physics. So maybe you can tell us new physics via this fascinating method. The other more modest comment is that I saw a lot of water hose or spirals in your previous slides, maybe even in the beginning, but at the core of these spirals, there was some fine structure that I'm curious to know what it is.
Okay, so
Are you with me?
yeah. Basically, I just chose this image because I've played with spirals before and they look really cool.
Absolutely.
I don't know that that's that there's any really phenomenal, interesting quantum mechanics happening here, but it does look really cool. And so I wanted to share that because I want this to be as entertaining a talk as it is a scientific one.
Very nice indeed. And can you connect the Möbius strip to the spiral? I mean, in your experience.
Yeah. This is something I want to try. Yeah, this is something I want to try, but I have to do it with a discrete time walk. I don't know how to get a graph Laplacian to I don't know how to get a graph Laplacian on just one of my dimensions to connect the other dimension twisted. Right, I'm not using a semi-direct product here.
One more fun idea for your high schoolers, and again, using your system to do conformal mapping and analytic mathematics, complex mathematics.
Yeah,
complex variables.
I suspect this is something that can be done. It's a matter of working out the mathematics ahead of time and being able to utilize the correct libraries. I mean, that's kind of it. Yeah, there's a lot of sort of background work that needs to go in before I start writing the code to do that.
For sure. Enjoying your talk. Thank you so much.
Thank you very much.
You're welcome.
Okay, there are some next questions. So maybe Mali can ask.
Okay, thank you, Mr. Pawel. Dr. Clark, I've enjoyed your chat, the presentation, and I put a comment in the chat. I want to draw a picture of Bitcoins, 21 million pixels, using this quantum works on graph. How could I do it? They should be separate, not like the spirals, because if they are connected, then they are not so they're not so clear.
I'm not.
But I'm interested in. You said you.
Okay,
are,
I'm not sure. You want to just
so,
use. You just want to use the Bitcoin image, or are you trying to actually do the mining of the blockchain with this?
No, I just want to do an image with 21 million pixels, just using quantum works.
Oh, okay. Hit me on LinkedIn. I'll give you some tips here, but definitely 21 million pixels. You may 21 million pixels. That means the image size is going to be roughly what, 3,000 by 7,000?
Yeah, I guess.
Something like that.
Yeah.
Oh yeah. You can actually do that. You can actually do that. That's it would just take a couple of minutes instead of one, but yeah. I've done images this large, so
Okay.
yeah. I would definitely break it up. You have one image, one set of images which are 3,000 pixels, and the other set of images which are 7,000 pixels, and then you can actually propagate it.
Oh, because I've done it in Paint, and it's like a 4 MB. It's like a 4 MB image.
Oh yeah, no problem. I mean, when I
like,
tried this, part of the reason I was doing it like in discrete walks, my very first NFT, believe it or not, was like doing a discrete walk on just a single dot, and the walking matrix was a gigabyte.
Wow.
And it was a shame to ask Python to do that. Python crashed a couple times. Poor Python.
And I have Python. I did Julia. I'm going to get Julia.
Or any language. I mean, there's a lot of good numerical languages which outperform Python. You know, basically all of them outperform Python. I just prefer Julia because its syntax is so similar to Python that it was like easiest to pick up.
All right, I'll hit you on
LinkedIn. F#, Rust, all super good options.
All right, I'll hit you up on LinkedIn and get that.
Great.
Okay.
Great.
Okay, Ron, now it's your turn.
Hey, Dr. Clark, good to chat with you. I think I heard you say you're in the Chicago area.
I am.
Yeah, me too. So I hope we can connect on LinkedIn.
Let's go get coffee.
Yeah, I heard you talk about lattice structures. Is there an application where this could be mapped to actual physical lattice structures like in Diamond or?
Yeah, absolutely. I mentioned Keeper I think is on the call. We're working on such a property. I mean, the hypothesis is that since it is a quantum mechanical system, right, we should be able to measure off physical properties just by the pure mathematics. I mean, one of the reasons I got into this, the person who taught me quantum computing originally, this is back in 2001, is Jean Bélessard in Georgia Tech, and his whole program was aperiodic solids in non-commutative geometry. And what he was doing, he's a physicist by training, I mean, but he does rigorous mathematics, and so he was measuring off these really interesting properties of aperiodic crystalline solids just using non-commutative geometry, and then they were later getting experimentally verified. But he had these rigorous results just coming off of a really good mathematical model. The same hypothesis should hold here. If we have a model of a graph which gives us some sort of molecular structure, we should be able to tune it in such a way that we can read off these actual physical properties just by the quantum mechanical system evolving on a graph. That's the hypothesis. I don't have any numerical results yet, but working on it.
Very cool. So do you think it would be useful for simulating and tracking, like in the diamond lattice, nitrogen vacancy centers and predicting interference between this spins of the centers with each other and spins with the centers in the base material?
Yeah, I suspect it will be. I don't have a good set of techniques to do that presently, but I suspect that should be one of the better uses for quantum walks on graphs after people get done playing with it for entertainment purposes.
That's very encouraging. I am doing some deep research on that nitrogen vacancy center stuff, so definitely have to look at your code.
Yes, I'm going to put I'll put it on here like moments after we end this call, but and I'll get with Pawel and Sebastian and get these videos out to you as well.
Thanks. Great talking with you.
Thank you.
Yeah, just a quick question, Clark. So thanks for the nice work and this impressive pictures made out of quantum. That's very interesting. So I was wondering if it's possible to add, for example, some external fields, and how smooth is that? If you wanted to make a paint or visualize a random walk with an external field inside.
Yeah, I've been thinking about this. Essentially, all of this has to go into the graph Laplacian, right? So the Laplacian, right, it's a free particle Laplacian. When you go back to the mathematics, so if you're just on a line, you have the function at vertex minus the function one vertex ahead minus the function one vertex behind. So it's a discrete second derivative, right? So that's a free particle. What function do you add on to mimic the correct potential in the Laplacian? Because then you have a Hamiltonian, and obviously you just evolve the Hamiltonian, e to the I Hamiltonian times time, right? And of course,
Right.
that would be for a stationary state. For a time-dependent one, that's the best answer I got right now. But the difficulty is not in understanding how it should be done. It's the difficulty in understanding how to add a potential so that you get a legitimate Hamiltonian trying to emulate the thing that you want to emulate.
Yeah, indeed.
That's the trick. But I mean, you guys are working on that at Molcat a little bit, I think, and I think it could be some interesting collaboration to be had in like setting up these graph potential energies and then walking across them.
Yeah, that would be great, and we can set up quick derivatives to express potentials and so on, and then we can have something quick to see how it looks like in the simulation.
I mean, let's try it. Let's try it. It sounds fun.
Yeah, yes, indeed. Yeah, thanks, Clark.
Okay, so let me remark. So in this MERF, I done a lot of this kind of problems. So lattice with defects for semiconductor model, external field for conductance model. So also if you would like, I can also help you with this kind of problem. So please contact me. In this case.
Okay, thanks.
Zajac, will you put your email in the chat as well, please?
Sure. So there are some my materials with my email. So okay, so let me put my webpage.
Yeah.
Great, thank you.
Fantastic. Do we have more questions or more comments? Thanks, Zajac, for sharing the link.
Dr. Babybird has a question. Why would anyone pay money for an NFT?
Well, okay. Let's go a little bit further away from quantum computing. This is just a take on cryptocurrency. Disagree as much as you want, right? I work on stock trading a little bit. I'm not aggressive. I just like the mathematics to it. Cryptocurrencies aren't currencies, they're stocks, right? You can buy them, sell them, short them. You can trade options on them, all that stuff. NFTs are like baseball cards, right? For example, I would never, ever, ever pay $1 million for Mickey Mantle's rookie card. I wouldn't pay any money for Michael Jordan's rookie card, really, and I'm in Chicago. I mean, I love Michael Jordan, but I'm not paying that much money for it. But I know people who would. I know people who would. And so in my portfolio, I have one NFT, and it's a friend of mine who made like a really nice mathematical art, and I think I paid her like $4, and I was like, you know what, this is cool, and I'm just gonna have it. Right. So it's why would you pay money for an NFT? Because you want to support the artist if you know them personally, or because you want to speculate, and there's a whole bunch of reasons. I mean, why do people take chances on anything? So I'm not justifying one action or another. If you think NFTs are a Ponzi scheme, you're probably right, and don't buy them. But you know, if you want to support the artist, you can also do that, and maybe they get screwed later because the value of their cryptocurrency drops too. I don't know. I'm just saying, like, I made them because it was sort of a fun thing, and at the time I was like, what? Why not use quantum computing for entertainment? Because no one's talking about like solving a max cut problem on a 3 regular Hamiltonian graph made out of 79 qubits. And who cares? Who understands what that even means? Here's a picture, as it were. Feel free to disagree with me.
All right. There was also a question about some other programming language that you can recommend besides Julia. Some participants declared that they will start learning programming in Julia. So that was a good
Well, it's funny. A friend of
recommendation.
mine, a friend of mine who's here in Chicago, he's one of the main Julia developers for OpenAI, and
Great.
his stated goal is to teach 1 million people Julia this year. And I said, I'll throw in 1,000. But I will say this. For data scientists, I've played data science a lot. If you understand Python and you have a little bit of experience with either MATLAB or R, Julia is going to be quite easy to pick up, and you're just going to be shocked at like how fast it is. The syntax is meant to be simple like Python. That's the point. But they've done a lot of more tricky, good backend developments. And so, you know, like with any language, including Spanish or Polish or Arabic or Farsi or Japanese, like the first few weeks are really, really frustrating. So, yeah. If you know Python though, your transition will be a lot easier. Other languages, you know, the next one I'm kind of looking at is Scala. I like that because it has this functional paradigm to it, but it's a little bit syntax heavy, and you know, just my company's not using it right now. We're in Julia, so I haven't had a good chance to play with Scala, but Scala, Rust, F#, I think are all really super interesting ways to go about in numerical computing. How does Julia compare with Fortran? I'm just reading this one. Julia's slower than Fortran, but you know, not that much slower. Here's the question: like, it's the balance of, it's the trade-off between speed and utility. And to my understanding, it's got the best balance of all the things. It's super freaking fast, and I don't have to worry about memory management. Right? C++, you still have to manage this, but you know, it comes in, you know, just a hair under C++ in speed, but its ease of use is like a lot easier to use, in my opinion. And I can be wrong. I'm wrong a lot.
All right. There was a comment that Rust wants to be the new C. That's interesting.
Yeah, I believe
yes.
that. I believe that's like Rust's main thrust, right? They want to overtake because they do some like really good memory management stuff, which is sort of above my pay grade. But Rust is a really interesting way to go. I mean, even for the Pythonistas here, Pandas is like so old and slow that the new thing that's like coming up quickly, I've been seeing this a lot, as polars, different type of bear. That's the Rust development for data frames. Right. So Rust is making some inroads, even though I'm not a Rustation, as they call them. It's a pretty cool way to go.
All right. There was also a question on the chat from Peter. There is a link to Archive, and he's asking if it is your profile. I'm not sure if you can check.
Let me
yeah,
look.
there are some papers about teaching quantum computer and probability distribution.
Yeah. So I wrote that one about quantum walks and graphs. I was applying to work in Oak Ridge's quantum machine learning lab. And I believe that paper contains the first image done by this technique ever.
All right. Good. Do we have more questions?
I also noticed there's a question. He asks, is there an article about transforming from 2D images to 3D images or videos?
Okay. Oh yeah. So here's my rebuttal question. When you say, so for me, the images that I'm dealing with are already three-dimensional. You have rows, columns, and colors. Right? Color is one of the dimensions. Or do you mean something that looks like a 3D image? Right, that's the question. So if something that looks three-dimensional, I don't know. When it comes to the third dimension being color or intensity or alpha, then this is just more of the same.
Yeah,
It's more of the same. You have to.
Yeah, I'm thinking about everything. It's color. It's colored, but I have, like, for example, like they can have a picture from different side or angles of an object, and I would like to combine them to make a 3D, like an image which will show a 3D picture. It's like something.
Oh yeah. Okay. So this what's the there's an open source software for this, and I'll have to look it up. I've forgotten what it's called. I had a guy on Fiverr help me with it at one point. Yeah, so that's not something that I have any expertise or specialty in. I just had someone like basically do it for me, and I paid him.
Thank you, though.
All right. Do we have more questions? Okay, I don't see more questions now on our chat. Clark, once again, thank you first of all, for the great talk and also for answering all the questions. It was very interesting discussion, and I believe that we learned a lot.
Yeah,
thanks.
I'll give one more plug. I think I have applied actually to give a version of this talk, a slightly more technical talk at JuliaCon, which will be in Eindhoven. If that comes up, then I'll let you know. And then so that will be a much more technical talk and much more about the Julia implementation and the mathematics behind it, rather than just like that. This is fun for play. But I've applied to give that talk, and hopefully they'll accept it and we'll come. And maybe Taha and I will go. We'll give you some more research when I go and hang out with them.
Yeah, that would be a great, Clark, to see you here in Eindhoven.
Yeah, it'll be awesome.
Perfect.
So if that comes up, then Pawel, I'll let you know, and you can spread the word. Of course, I'll LinkedIn it everywhere.
Great, fantastic. That's a great news. Okay, and with this, we would also like to thank all our participants for very interesting questions as well, and your engagement in discussions. And we are looking forward to our next meetup, and we hope that we'll see you next week. Well, thank you, everyone. Have a good weekend. Thanks, Clark, once again.
Thank you very much.
Good luck in
I hope to
Eindhoven.
connect with all of you soon.
Perfect. Thank you.
Yeah, thanks, Clark.